In this section, 5.3, we're going to look at some of the tests that we can use to decide if a series is convergent or divergent. They're not always conclusive, so we have to have a few different tests, but the first we'll look at is the divergence test, which is a pretty simple test for divergence. Either tells us that the series is divergent or keep looking. It's never going to tell us that a series is convergent. The integral test is also in this section. It's a little bit more powerful in that it can tell us either if a series is divergent or convergent, or maybe it can also be inconclusive. It doesn't apply to all series, but it's much more flexible than divergence test. And then a special kind of integral test is the p-series test, which really it comes from the integral test, but it's very easy to use. We're going to start with divergence test. And the divergence test, you can look in the book for a detailed version of it, but I like the simple version, which says if the limit as n goes to infinity of an, so the limit of the terms, is not equal to 0. So if this is so, either it's equal to a real number or equal to infinity, or the limit doesn't exist. If any case other than 0, then the series from n equals 1 to infinity of an, the sum of all those terms of the sequence an, diverges. And I think the easiest way to understand this is if the terms, well, if the series does converge, those things have to get smaller and smaller and smaller and smaller and smaller and smaller, closer and closer to 0. In fact, the limit has to be 0 for this to converge. So if the limit is not 0, then it is not convergent. In other words, it diverges. Let's see a few examples where we can apply this. The first one, so this is example 5.13, if you want to look at the detailed solution in the text. We're going to apply the divergence test first to the series sum from n equals 1 to infinity of n over 3n minus 1. So the terms, the an, say my an are n over 3n minus 1. You could work out several terms of that, but working out finitely many terms, you still can't tell if it converges or diverges. Of course, a finite number of terms is going to add up to a finite real number. But all infinitely many of the terms in the sum, well, we can use the divergence test here. The limit as n goes to infinity of an. We're going to look at the limit of just the terms of the series, the sequence, which is the limit as n goes to infinity of n over 3n minus 1. This one you can algebraically rearrange it. Maybe it might be easier to use L'Hopital's rule. But this limit is going to be, yeah, I did use L'Hopital's rule in my work here. So you can see that as n goes to infinity, well, n goes to infinity, but also 3n minus 1 goes to infinity. This is an infinity over infinity situation. So I can use L'Hopital's rule, and it's the limit as n goes to infinity of the derivatives, the quotient of the derivatives. Derivative of n is 1, derivative of 3n minus 1 is just 3. And that, the limit of 1/3 is 1/3. So I'm going to put my conclusion up here. Well, that is not equal to 0. So I can conclude that the series itself diverges. So that limit being equal to 1/3 implies the series. So the sequence converges, that's fine, but it doesn't converge to 0, so the series diverges. And that's my answer there, that diverges, or divergent is the result. So I've got a limit that's not equal to 0, therefore the series diverges. Let's look at one more example. I'm going to use this test again, this time, still example 5.13. This time we'll look at part B, which says to apply the divergence test to the sum from n equals 1 to infinity of 1 over n cubed, 1 over n to the third. And so my sequence, my terms are 1 over n to the third. And you could list those out for n equals 1, it's 1 over 1 cubed, which is 1. For n equals 2, it's 1 over 2 cubed, which is 1/8, and so on. But what we really want to look at is the limit as n goes to infinity of an. And if we can find that, this is the process of using the divergence test, this is the limit as n goes to infinity of 1 over n cubed, which is, as n gets larger and larger, this expression, this denominator gets larger and larger, but this expression gets smaller and smaller, with a limit of 0, and this doesn't really tell me anything. What it does tell me is the divergence test is inconclusive. So the divergence test doesn't tell me that it converges or diverges. It's inconclusive. There's a part C for this example that has another series for us to look at and test with the divergence test. For part C, we're going to look at the sum from n equals 1 to infinity of e to the 1 over n squared. So my terms of my series, my an, that make the sequence e to the 1 over n squared. So for n equals 1, of course, I put in 1 there, e to the 1 over 1 squared, or e to the 1. That's just e. For n equals 2, I've got e to the 1 over 4, or e to the 1/4, then e to the 1/9, so on. What we really need to look at, though, is the limit of, as n goes to infinity of this. I'm going to write this one a little bit differently, just to show the reasoning a little more clearly. First of all, as n goes to infinity, what happens to 1 over n squared? I'm really just looking at the numerator, the exponent here. 1 over n squared goes to, the n is getting larger and larger, so n squared is also getting larger and larger. My denominator is growing, and this is going to 0. All right? And I'm not using the limit notation because I'm writing so many different limits here, but if the numerator is going to 0, what's the whole expression going to? Well, e to the 1 over n squared is going to e to the 0, because the exponent is going to 0. Well, that's just 1. E to the 0 is 1. So the terms of my sequence here are approaching 1, they're not approaching 0. That's the important thing. If they're not approaching 0, this implies that the series diverges. And that's my answer. It diverges by the divergence test. Because the terms of the series don't go to 0, so the series diverges. All right, so that's the only thing that the divergence test can tell us for sure, sometimes, is that a series diverges. It cannot tell us information about actual convergence. This next test, though, is more powerful in that sense. It can tell us sometimes if a series diverges, sometimes it can tell us if a series converges also. But there are cases where it's inconclusive, or cases where it just doesn't apply. For this integral test, the integral test, we're going to look at a motivating example that shows kind of why the integral test works. I'm not going to do a proof. I'm not even really going to use the partial sums that we have for the definition of convergence and divergence. We're going to look at a familiar series, but we're going to compare these two things, the harmonic series sum from n equals 1 to infinity of 1 over n. We've looked at this before. This is going to be a more graceful way of dealing with it, but it is something we've seen before. In other words, that's 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, etc. The sum of the reciprocals of the positive integers. So we're going to compare the harmonic series and the function f of x equals 1 over x on the interval from 1 to infinity. So I don't want to fuss around too much with this function close to 0, but I'm only looking for positive values of 1. It's continuous. It's got a really simple shape. It's getting smaller and smaller and smaller. It's a hyperbola if you look at the graph. But so that's what we're going to do for a motivating example with the integral test. And I'm going to have to clear this off to put these two as graphs, but you'll be able to tell them apart. Think of the harmonic series as a bunch of individual numbers that we're adding together. And I'm going to write them on a graph where I'll start with 1, 2, 3, 4, 5, 6. That's probably enough. And I'm going to make squares here. I want to just have my 1 high enough that we can see. Okay, that's actually a square. It's 1 wide and it's 1 tall, so it's a square. But it doesn't look like a square. It's because my scales are different. But it has an area of 1, definitely. It's a width 1 and height 1. So I'm going to label this one down here with 1. I don't want to clutter things up, so I want to label the areas at the bottom. And my next square is going to have a height of 1/2, with a width of 1/2 still, so its area is 1/2. And my next square is going to have a height of 1/3, and then my next square will have a height of 1/4, and they're getting smaller. but you can probably recognize now what these numbers are. They're the terms of the harmonic series. 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. And there will be more of these. I'm not going to go much farther with my picture, but now the other thing, this is my representation of the harmonic series. This is right at 1, 1. 1 over 1 is 1, so 1, 1 is a point on the curve. But the left part, we're not going to use this. To the left of 1, the curve 1 over x, which was my function, it goes up like an uses the y-axis as an asymptote. Now to the right, it comes down and assumes values that it kind of has in common with these rectangles. X equals 2, y equals 1/2. And there's the value of 1/2. X equals 3, y equals 1/3. X equals 4, y equals 1/4. X equals 5, y equals 1/5. And so on. And that curve kind of follows along with the, I guess, the left top corner of each rectangle. Now, which one has greater area? Under the rectangles or under the curve? Well, if you look at a finite number of them, you can see that there's these leftover parts. So the rectangles have greater area. I'm talking about the limit. We want to add up all infinitely many of these rectangles or integrate the area under the curve from 1 all the way down the number line, again, to infinity. So what we're going to look at, this is the reason, the area under the curve is less than the area of the rectangles. Now, again, that's if I look at a finite number of them, it is less than. In the limit, though, we can't be too sure about it. I'm not sure that they're going to be equal, but they end up being essentially the same thing. So what we're going to look at is the area under the curve from 1 to infinity, and it's going to turn out to be infinite. So if that's infinite and this one is larger, then this one is definitely also infinite. So here's space. All right, so the area under the curve I can write as an improper integral from 1 to infinity of 1 over x dx. That's the curve I used, 1 over x. That's my f of x. This is an improper integral, so we need to evaluate it by backing off from infinity to some finite number b, and then taking the limit as b goes to infinity for that finite domain function integral. Also, I'm going to write 1 over x as x to the negative 1. It's really not going to help because I can't use the power rule here, but I do that anyway. But negative 1 is the exception to the power rule for integrals. The antiderivative of 1 over x is natural log x. We don't do the plus, minus, plus 1 and coefficient stuff here. So let's go back up to the top. To finish evaluating this integral, this is the limit as b goes to infinity of, I can do my antiderivative here, it's natural log of x from 1 to b. So I just evaluated this ordinary definite integral over a finite interval 1 to b. And fundamental theorem of calculus gives me that that's equal to the ln of b minus the ln of 1, which is the limit as b goes to infinity of ln of b. Ln of 1 is 0. Now the natural log curve, the limit of ln b as b goes to infinity, ln doesn't level off. It keeps going up and up and up. Therefore, this ln of b keeps going up and up, and the limit is infinite. Now remember, the area under the curve is less than or equal to the area of the rectangles, and we just saw that this area under the curve is infinite. Therefore, the area of the rectangles has to be infinite. And what this implies is that you could kind of say that it equals infinity, but really it diverges. It's not a real number, and it's not a sound, it's a good and useful mathematical expression, but it doesn't mean a number. It's not going to be useful in further computations. But this is the spirit of the integral test. We find a function that's related to the terms of the series that we're working with, and instead of trying to look at the partial sums specifically, we just look at the integral of that function over the right half of the number line, from 0 to infinity or 1 to infinity more typically. You can actually start from any finite point. If you're going to infinity, they're going to have the same convergence. I like to go through a simpler version of the integral test, but if you want the full version, the textbook has that in there. I want to look more quickly at another example of where the integral test, or the idea of the integral test, can give us the convergence of a series. We saw a divergent one just now. Here is another motivating example. We could compare the sum from n equals 1 to infinity of 1 over n squared which is 1 over 1 squared is 1, plus 1 over 2 squared is 1/4. 1 over 3 squared is 1/9. 1 over 4 squared is 1/16. 1/25, and so on. It's the sum of the reciprocals of all the squares of the positive integers. So you can see those squares. This denominator isn't there, the 1, but 4, 9, 16, 25, the squares. We're going to compare this series with the function f of x equals 1 over x squared. This isn't completely new. We did something kind of like this with sequences even, but using it in this way, we're not really comparing the functions. They're the same. What we're going to do, though, to answer a question about the series, the infinite series, we're going to look at an integral, or an area under a curve for the corresponding function. These ones would look like this. If I graph them, I'm just going to do a sketch. 1 over x squared is like that. It looks similar to 1 over x. It's just that it does get smaller faster. There's 1 over 1 squared is 1. So that's a point on my graph. And then 1 over 2 squared, oh, this isn't very, okay, the book picture is a lot better because my rectangles really aren't getting small enough fast enough. But what they do is they put that first piece of the first term as a separate piece, and then we start looking at a rectangle of area 1/4, and a rectangle of area 1/9, and a rectangle of area 1/16. And in this case, if you set it up like this, the curve is above these blocks. So the area under the curve is greater than the area of the rectangles. Let me write that out. The area under the curve is greater than area of rectangles. Sorry about the squish there. But really, we do need to say that it's greater than or equal to. And I'm not talking about this piece of the area. We're really just leaving that as a 1 for our first block, and we're looking at the area under the curve from here, starting at 1, going all the way down the number line. This part actually is not finite. It's not very useful because it's not a finite area. But if we start to look at the integral from 1 to infinity of 1 over x squared dx, that's the area that's larger than the area of the rectangles. That's an improper integral. I'm going to have to do the limit as b goes to infinity of the integral from 1 to b of x to the negative 2 dx. And here I do use my power rule. The antiderivative of x to the negative 2 is negative x to the negative 1. And that's evaluated between 1 and b. See, if I do the power rule on here, I bring down the negative 1, it cancels the negative, I subtract 1, I get x to the negative 2 with no negative. All right, and I'm about ready to evaluate that limit even. It's the limit as b goes to infinity of b, so that's negative b to the negative 1 minus negative 1 to the negative 1 to the negative 1. And that's really just the limit as b goes to infinity of negative 1 over b plus 1. And that limit we can evaluate as b goes to infinity, 1 over b goes to 0, and all that's left is this 1. Now, I'm not saying that the area is equal for the sum of the rectangles. That's the series that we're looking for. We didn't find the value of that series. We found the value of the integral, but since the rectangles are below, what we do know is that the area under the rectangles is less than or equal to 1. In particular, it's convergent. So what this implies that the series that we were looking at, the sum of 1 over n squared, so not the harmonic series, these ends are squared. The sum of the reciprocals of the squares is what this one is convergent. And that's the kind of thing that we want to find from the integral test. Either it's divergent or convergent. We can't always use the integral test, but when we can, it gives us one of those answers. We do have to be able to evaluate the integral. If we can't evaluate the integral, we really aren't going to be able to do the test. So I like to stick to simpler integrands, simpler functions. But if your series has complicated terms, you might have to do more than that, more than the integral test. So next, let's look at what the integral test says in a way that we can use it without having to go through graphing. And you might have noticed the divergence test, once we started using it, it was pretty quick. We did 3 examples quickly. Integral test is not quite as quick, but here it is. This is not an integral test. This is the integral test. And it says if a series from n equals 1 to infinity of an has an greater than 0. In other words, the terms are positive. Not negative. That 0 wouldn't make much difference because you'd be adding 0, but we'll look at alternating with positive and negative series later on. For the integral test, these need to be positive. And for the 2 motivating examples, the functions were positive also. So if the terms are positive and f is a positive, continuous, decreasing function with f of n equal to an. So these are the 3 conditions. The function has to be positive, continuous, and decreasing. The ones that we looked at were our other examples will. If it's not, then this can't be used. But this is the main thing. The function is the same as the terms of the series. I would usually say f of x, because I can plug in a real variable. And I will to do the integral. But it's the same as the an, the terms of the series. So that was the case in both of those examples. Here's the conclusion. Then the sum from n equals 1 to infinity of an and the integral from 1 to infinity of f of x dx either both converge or both diverge. Another way to say that is that they have the same convergence property. They converge, or they don't converge. And what we're going to do is evaluate the integral to see if it converges or diverges. If it's a converges, it's a finite number. Diverges, it's not a finite number, or the limit doesn't exist. This will have the same convergence. Now, this seems really specific, but a lot of terms of series have these properties when you write them as a continuous function or a function of a real variable, positive, continuous, and decreasing. If they weren't decreasing, they're not going to converge. You could use the divergence test. A continuous function is usually not hard to get by replacing the variable n with the variable x. You have to watch out, I guess, for asymptotes in a rational function or something. But and then positive, well, we're going to have to get more sophisticated techniques to look at series when they oscillate between positive and negative. For now, though, we're looking at positive mostly. So this is the test. We're going to look at a few examples of how to use this. And you'll see that applying the test is much quicker than those first 2 functions that I graphed and tried to explain why. Here, we're just going to use the test. We've got to put some checks in some boxes, though. We've got to make sure our function is positive, continuous, and decreasing for this to apply. Here's an example from 5.14 with the series, the sum of 1 over n cubed. We're actually going to see a very quick way to to find the convergence of this at the end of the section. For now, though, I want to use the integral test because that's why the other test works. So this is some justification for the next thing too. Now my an is 1 over n cubed, and the function f of x equals, now I want that as a function of x, 1 over x cubed. That function, and we're really just interested in it on 1 to infinity. I know this function isn't always continuous, or even always positive, but on this interval it is, and that's the only place it matters, because we're summing from 1 to infinity, we're going to integrate from 1 to infinity. This is a discrete variable, 1, 2, 3, 4, 5, 6, 7, etc. This is a real variable, can't count them, it's just 1 to infinity, but this function is positive continuous and decreasing. And if you're checking a function for that and you write them down, I recommend abbreviations so you don't write out the whole words, but checking those three things, think about it with this function, maybe even look at a graph of this function on Desmos or a calculator to see that it's positive, continuous, and decreasing. Again, only matters on this interval. The other thing is that f of n equals an. If I plug in n in place of x, I get 1 over n cubed. Well, that's really the point. It's 1 over n cubed, which is the general term of my series. So we're ready to begin. Okay, this is the beginning. But what we really need to do for this test is look at the convergence of the integral from 1 to infinity of the continuous function. So we're trying to find an infinite sum, and not evaluate it, but find out whether it converges or not. So we're going to look at an improper integral, an integral over an infinite interval. And that, the integral test says that they have the same convergence. So I'll look at this. The limit as b goes to infinity of the integral from 1 to b of x to the negative 3 dx. And that's the antiderivative. I'm going to have x to the negative 2, because I'll subtract 1 from the negative 2, I get negative 3. But I also need to have a negative 1/2 coefficient, because when I take that derivative, I'm going to bring the negative 2 down. The negatives will cancel, the 2's will cancel, and I'll get my x to the negative 3. This is between 1 and b. And then this is the limit as b goes to infinity. I want to plug these bounds into my formula here. It's negative 1/2 b to the negative 2 minus negative 1/2 times 1 to the negative 2. You could factor out this 1/2 out of both expressions here and factor it out of the limit even. What really matters here is as b goes to infinity, b to the negative 2, which is 1 over b squared. In fact, why don't I do that? Let's factor out the negative 1/2 just so we can focus on the limit as b goes to infinity of 1 over b squared minus, I factor out the negative there, 1. Now this part, since b goes to infinity, b squared goes to infinity, and its reciprocal goes to 0. So all that's left is -1. -1 times 1/2 is 1/2, which is the number isn't so important as the fact that it's a number. It's a real number. It's not infinity, and it's not a limit that doesn't exist. This integral, the integral converges. And because of the integral test, I satisfied the conditions for my function f, and I found that the integral, the improper integral converged. That means the series sum from n equals 1 to infinity of 1 over n cubed converges. And it's good for, well, that's what we're looking for, it converges, but by the integral test. So here I'm not only saying the answer, which is convergent, series converges, but also why. The reasoning that I'm using is the integral test, and that's a good thing to note in your answers. Next, I'm going to get you started on part B of this example. And you can use the book and finish it up for practice. But part B has us using the series 1 over the square root of 2n minus 1. Yeah, that's fine. So you have to be a little bit careful that we don't get a 0 in the denominator here, but we won't. If n starts at 1, 2n is 2. Minus 1, that's 1. And we don't have a 0 in the denominator. For larger values of n, it's going to be even larger. I mean, the denominator will be larger, but it won't be, you won't get a 0 in the denominator. The an here, I'm going to write them like this, 2n minus 1 to the negative 1/2. So negative, because it's in the denominator, but 1/2 power is the square root. It doesn't matter too much how you write it at this point. But my function, f of x equals 1 over square root of 2x minus 1. Same as the terms of the series, just I'm using the x variable. Thinking of it as a continuous function. It is positive, continuous, decreasing on 1 to infinity. And so what I would look at is the improper integral from 1 to infinity of 1 over square root of 2x minus 1 dx. I don't want to take the time to do this, but I'll get you started with it. You can finish this. This is a u sub integral with u equals 2x minus 1. Du would be 2 dx. But then you can swap everything out. So using that substitution, you can do this integral. It's a power rule. Negative 1/2. U to the negative 1/2. And then you're also going to need to, after you write this as a limit as b goes to infinity of the integral from 1 to b, you're going to need to change these bounds to u values. These are x values, so you need to change them to u values. But there's more to that, of course. You've got to do the u substitution to evaluate the integral. Then you have to take the limit of that expression as b goes to infinity. And what you're going to find is, I'm going to do it as a equals ... equals what I did, it took me 6 steps to get to that's equal to infinity. It ends up not being convergent. The improper integral here is not convergent. And that implies that the series is divergent. Or the series diverges, again, by the integral test. So we built an integral from the form of the terms of the series. Of course, it's an integral. We want to write it as a continuous function rather than a discrete function. But then we evaluated that. It diverged. The integral test tells me that because it satisfies the conditions, the series also diverges. All right. And now the good news. The p-series test is going to give us a way to tell the convergence or divergence of a broad class of series with very little work. So, p-series. First of all, before we get to the p-series test, for a real number p, the sum from n equals 1 to infinity of 1 over n to the p is a p-series. So this definition, p-series, the p is lowercase even in its proper noun of the name because we're using a lowercase p as the symbol, and it's p for power. Now, this is not a power series. Power series is something else entirely. The p series has the exponent p on the base n, where n is the variable of summation, or the index. So index to the power p. Well, 1 over that gives me the p series. And let's look at some examples before we look at the actual test, because we've seen these before. Here's the sum from n equals 1 to infinity of 1 over n. Well, you don't see the p there. You don't see the p because it's 1, n to the first. P equals 1, and this is the harmonic series. And if you'll recall, it diverges. Harmonic series diverges. Another example that we've seen is n equals 1 to infinity of 1 over n squared, the sum of the reciprocals of the squares. We saw that earlier today, and I think we saw that in 5.2. This has p equals 2. And with p equals 2, in this case, this converges. As we've seen before. We just had an example with the integral test of 1 over n cubed. That would be p equals 3. We also, actually, I'm not sure if we've seen this one, but I do want to mention this one. The sum from n equals 1 to infinity of 1 over the square root of n. Now, it's not written really as a p series, but this is 1 over n to the 1/2 power, and that's p equals 1/2. That diverges. And I'm not saying why on these yet, although we've seen a couple reasons why this one diverges. We've seen at least one reason that this converges. This one diverges. We're going to see why based on these p values when we look at the p-series test. And the p-series test is pretty simple. It works like this. The sum from n equals 1 to infinity of n to the p, I'm not going to say equals, but let's use the two-story brace to see the results. It converges if p is greater than 1, and it diverges if p is less than or equal to 1. It is kind of a simple form, but it's a very simple test. If that p is large, in other words, that exponent on the variable downstairs is a large number, these terms are going to get smaller quickly enough for the infinite sum to converge to a finite number. Now again, it's not telling us what that number is, but very often it's enough to know that the series is convergent to be able to use it. If the number is not large enough, if it's less than or equal to 1, and this includes negative numbers, anything less than or equal to 1 is going to give me a divergent series. For example, for 1 over n to the first. The sum of 1 over n to the first, or the sum of 1 over n, that diverges. That's the harmonic series. If I have a smaller power, smaller than 1, for example, 1/2, these terms just are not getting small enough, fast enough for the whole infinite series to converge to a finite number. I've got a couple examples that we can look at to see how to apply the p-series test. The first one, these are 515, and the first one is the sum from n equals 1 to infinity of 1 over n to the fourth. So p is equal to 4, and that's greater than 1. P is greater than 1. So the series converges. A second example, part B, says the sum from n equals 1 to infinity of 1 over n to the 2/3. What that means is n squared, and then we take the cube root, or the cube root of n squared, or you can do the cube root of n squared. Either way will get you n to the 2/3. But the point here is that p equals 2/3. 2/3 is less than or equal to 1. It's less than 1. It's less than or equal to 1. That means, that implies that the series diverges.